can you hear me online?
Yes.
Thank you. Okay, so you should all have received your marks back from the in-class and the homework assignments now, so you should all be able to see those on Canvas. If not, you either didn't submit it or I've missed it somehow, so let me know if it's not up there. So what I'm going to do today is go through the answers to those questions just so you know where they are, and then what we'll do is we'll finish off hopefully the next section 5, we'll complete that. And actually we're not that far behind, we're actually pretty close to where we should be. I realize there is not a timetable as such, and that was done on purpose just because it's really hard to keep up with how you fall behind with these classes when we're doing this hybrid format. So I will try certainly by the end of the week to get some kind of schedule in hand. Now I know what's going on and how long it's taken us to get through things, because by I think October sometime we'll have a midterm scheduled. Okay, so let me just share the screen. I've also lost my Apple Pencil, so I will not be writing anything until Wednesday when I get the replacement through. And also a reminder is that I have office hours today, so if there's anyone who needs to see me, I'll be available between 12 and 1. Okay, let me just get this assignment up so I can go through it. But what I've done is took out the different PowerPoint presentation sheets to show you where the answers were, so that you can see that they were in the notes. So first we'll go through the in-class assignment here. So the in-class assignments are actually generally just to let me know that you're reading the notes. They shouldn't be that difficult. And then the homework assignment should take a little bit more time where you may have to look around for the answers. But again, they shouldn't be overly difficult. But if you are struggling with those, obviously you can come and see me and put you on the right path. But then the in-class, I'm still trying to work out what the format of that will be. And there's several new strategies that have come out for monitoring you taking the exam over Zoom. I'm having a look at those, although some of them seem pretty comprehensive, the amount of lockdown on your computers that you have to do. So we'll come up with some kind of method for that. But I think we'll still restrict it to the 50 minutes you're in class, right? Rather than having it as a take-home assignment. So it does qualify then as an official exam done in the time here, okay? But we'll see. I'm still playing around with that. So bear with me while I have a look into those things. I know a lot of people are going online and locking down computers. I don't want to do that really. So question 1 on the in-class assignment was, in general terms, how many repeat units does an oligomer have? So it was 2 to 10, 10 to 20, 10 to 200, or 200 to 1,000. The answer is on here. So this was taken from the first lecture, right near the start. So it's 10 to 200. And the second question was, which of these artificial devices are characterized as endoprostheses? So you have artificial skin, artificial limb, and artificial graft. Anyone know which one that is? Silence. You all answered it pretty well.
The graft, artificial graft, and the
yeah, the graft is right. Okay, that's good. And then give 2 disadvantages of using metals and alloys as biomaterials. And the disadvantages are over this side. So that was a little bit later on in lecture 1. So corrosion, dense, and difficult to process and fabricate. So some
question, Dr. Maybot.
Yeah.
So I don't know if this is just being too picky, but when it comes to metals and like having corrosion, if you create a metal like that's corrosion resistant, such as like adding chromium, does that still consider like a disadvantage in this industry?
Well, if it's not going to corrode, then it's probably not a disadvantage. I think the main thing is that I think the ones that contain steel and iron are susceptible to corrosion. So you do have to treat it with something, like you said before, add some doping agent like chromium or whatnot to it. But then that can change the way that it is processed and fabricated. So not all these disadvantages stand for everything. And these are just a selection of disadvantages which occur commonly within using metals and alloy devices.
Okay, cool.
Okay. So then we also had that ceramics are occasionally used as acetabular cup liners. Name a polymeric alternative. The polymeric alternative is ultra high molecular weight polyethylene. And the reason behind that is that the ultra high molecular weight polyethylene shows less wear than the ceramics, and they're not as brittle, so they last a lot longer. I had some people put a justification that they'd want something to be biodegradable. In this situation, you definitely don't want your cup liners to be biodegradable. That's not going to be a good outcome. It means you're going to have to replace them quite often. Name 2 processes that occur within the body that are responsible for the breakdown of biodegradable polymers. So there are enzymes and hydrolysis, or small molecules in there. So they're the 2 that we selected. Give 2 examples of natural polymers. There's lots of natural polymers, but there's a list on that. I think it was like the second slide in, which gives a list of all the different polymers we have within our body, but things such as DNA, protein, straightforward. Which chemical moieties are used to form crosslinks that occur during vulcanization? So the crosslinks are formed using the thiols in there. Now I think I haven't checked everyone's paper, but I it has to be specifically thiols, right? And some people use some weird terminologies for describing thiols that aren't correct to the functional group. So it's really important we get our functional groups correct. So you will lose marks if you don't get that functional group correct. Name 2 of the 5 copolymers. So we know statistical is one that's not shown on here, but you have random, alternating, block, and graft. Name the following copolymer according to the structural nomenclature. It's actually this one here. So I've got written on that page, answer to question 9 is the graft copoly AB. And the important thing is mainly that you got the A and B the right way around, right? So A is first because that forms a backbone, and B is the side chains off that backbone there. Give a disadvantage of using biodegradable polymers for arterial strength. So one of the disadvantages is that they can recoil and collapse. Name the polymer formed by the monomer in the image. So the important thing is that this is getting to the terminologies and the naming systems in there. So we're doing source-based naming for this one. The answer to this is polyethylene oxide, not polyethylene glycol. There's still some people that put polyethylene glycol in there, and that is incorrect. So just know the difference between those two from the source naming systems. What is a name given to the reactive end groups that are capable of contributing to further polymerization? And they are called telecalic claws. I think that's the way you pronounce it, but that's what they're called. So they can undergo further reactions to extend out. Which of the following are properties of thermoplastics? You can select more than one answer. So the 2 there that I've starred in red are that they can be heated or made to flow, and that they can be reshaped. The rest are properties of thermoset polymers in there. Name the pendant side group on this polymer. So this one's a little bit more tricky, but this is, you can see it on the table. This was at the end, I think, of lecture 2, in fact. I think it was lecture 2. So you can see that it's polymethyl methacrylate. That is a methacrylate group that is on that end there. Ring opening polymers are formed by which polymerization kinetics? So that's chain growth. Actually, I don't think I've written that one on here. No, I've missed that one off. How is step growth polymerization most commonly terminated? So it actually isn't terminated. It just stops when because the monomer functional groups are consumed. So there's no termination step for there. What is the molecular weight of polyethylene? N equals 5,000. So I actually got that 140,000 on there. Calculate the degree of polymerization for 95% conversion. So that's 1/1 minus 0.95, which should be 20. Some people put percent at 20% on the end of those things. It's not 20%. It's just the degree of polymerization. So it's just a number of consecutive monomers in that chain. Name one method of providing the energy needed to initiate a free radical polymerization reaction. So the 2 methods are there. They are UV light or heat. The activation of free radical polymerization results in what type of cleavage? It's a homolytic cleavage. So that's right next to using UV light and heat. Why are free radical initiators not strictly catalysts? And this is a common one that some students get confused with, or certainly have been confused with in the past. They call the initiators catalysts when they're not. It's because they get used up in the reaction, so they don't get recycled. So they are not strictly catalysts. They are strictly initiators. So name this initiator. Its abbreviation is fine. So that's AIBN. So one in the middle there. What type of termination of free radical chain polymerization occurs when 2 radicals react together? So I think that one, oh, there you go, it's on this one. So when the two radicals react together, we get combination. So that's your answer for there. What polymer transition state does Tg represent? And we've come to that now in our lectures, but Tg represents that transition from a glassy to a rubbery state. 25 was, what is a shorthand notation for viscosity average? No need for the X bar to be added. And there you go, it's just MV. So that is, they are fairly straightforward, I think. Let me just check. I can tell you what the average score was for this. So yeah, so the average score was 94% for that, so it's good. So they're a good opportunity, some of the in-class assignments, to pick up some good marks, because we're really just making sure that you're going through the notes, which is vital for when it comes to your midterms. So now I'm going to look at the assignment that we did for the homework assignment. So I'm not going to go through all of these, but I'm going to tell you what some of the common mistakes were with this. One of the common mistakes is that people don't read the question. So make sure that you understand what is needed from the question to begin with. There is particular parts in there that you need in there, but you need to include things such as, you know, the zigzag and things like that, because that describes the different sequences of the polymers in that polymer in the chain. So it's really important to have those things in. So most people got, I think, A and B correct, and C. Although I will say some people are still getting confused between the functional groups and having the double bond in there. So if the double bond is in there, I'm going to tell you it's most likely going to react through that double bond. So if you see a functional group and there is double bonds in there, choose a double bond first if you're totally unsure about what's going on. So people have drawn some quite elaborate designs for how those carboxylic acids react with each other, but that's not what we're looking for in that case. So then D is pretty straightforward. It's a polyamide formation, so it's carboxylic acid reacting with the amine. The interesting thing about D is that you've got one molecule which is bifunctional, so it's got both groups on it, which means it can react with itself under the right conditions in order to form a polymer chain. E was pretty straightforward for everyone in forming a polyester. And again, F is a surprising one because it looks pretty complex, but most people get that fairly well. G is a little bit different, and it's a little bit different because we have these chlorine groups on top of our C double bond O, which means that actually when we have a small molecule come out, we actually lose HCl in this case rather than water. It's basically replacing OH groups on the Cl replaces the OH groups in there. Again, most people got H correct. I was another tricky one for some people, just because it looks like it's got that functional group on the bottom end there. Don't get fooled by the functional group, because it's not one that we've really told you about in any reactions. So it's important that when you see that functional group on the end that's that long, is that unless it's a carboxylic acid or an alcohol and there is another alcohol carboxylic acid to react with, that you probably go for the double bond in there and extend that one out. So it's a chain polymerization.
Dr. Mabit, I had a quick question in general. So as I was doing this, I was wondering, when we're doing the condensation reactions, would the moles of water be N-1? Are we just simplifying to N?
So it depends on how many functional groups you've got on the outside of your molecule, right? So in the case of G, for example, there'll be two HCl come off to make that polymer.
Right.
Does that make sense?
Mhm.
But then for some of the others, when you've got this one, D, which is
Yes.
bifunctional there, you're only going to get the one water coming off because it just reacts with its own end groups.
Right. I was asking, would it be like N-1 since you would need two molecules and you would only get one water out, so there would always be like one
Oh,
less.
yeah, that makes sense. Yeah, that makes sense.
Okay. So should we always just write N anyway?
Yeah, I mean, how I see it is that if you write there is a byproduct coming off, then generally you'll get most of the marks. The number of byproducts isn't really as important to me.
Okay. And also I saw that we had there was like an H or an OH written on the outside. Is that something part of the structure?
No, that doesn't matter. That doesn't matter. Some people like to write that. Some people don't like to write that. Although I will say, that's a good point. Some people write that inside the bracket, and that is not correct. It has to be on the outside of the bracket.
Okay. Thank you.
Okay. So then J is a good example of where you need your zigzags in there, right? Because you don't know the orientation, you don't know the stoichiometry of this reaction, so you won't know the order in which these things polymerize together. So by putting the zigzag in there, it's acknowledging that we don't know that order, okay? And then K is the same, right? K is a different reaction, it's stepwise, but we still need those zigzag lines in there in order to show that there is a difference between those, the way, we don't know the way that they would polymerize together. I think most people, so yeah, the last one actually you shouldn't have lost any marks for. That's a bit of a confusing one. There needs to be a bit more information there, although actually most people got it correct, but I just left it because we need some more information in there. In fact, I think it has to react with anhydride or something at this stage. I haven't got it written down, but I left that one out, so everyone should have got that mark for that. Then classification is fairly straightforward. So I think if you got the answers right to the first section, you definitely got the answers right to the classification section. If it is addition, it's chain, and then if it is condensation, it's step growth, and that follows all the way through. So I think there's a few where people have got a little bit confused, but I assume that most people who got the first bit right would have got this bit right as well. So then we had the different blanks. So we had to fill in the blanks for the appropriate linkage and family name and list of polymer. So again, most people did pretty well to that. Some people leave out letters, which was a little bit confusing. I don't know if they got confused with what letters they'd put in. But if you left out a letter, then you would lose a mark. And again, similarly, if you put the letter in the wrong place, you'd lose a mark as well. But for these things, just make sure that you write in as much as you can. And then draw 3 consecutive repeat units of polyhydroxy valerate and PHV, and carefully circle all the ester linkages. Now, people drew the ester linkages on the end, so you can see there you've got the I can't point out with a pen because I haven't got one, but if you see there's this, I can't even write, there's a CO and an O on the terminal ends of that. That is still an ester group, right? So outline that, and that shows that I know that you know that this is continuous and it's a polymer, right? So you should outline those ester linkages there. And then draw 3 consecutive repeat units of a polymer formed by the ring opening polymerization. And so again, if you got those units correct, you get correct structure, you will get 1. And then if you circle the correct linkage, you would get 1 as well. But the important thing is if it's on the ends, that's still part of a linkage. So make sure you circle that in there. So then draw the structure of the monomer used to produce the polymer on the end there, and then The A is via step growth polymerization. So you have to have a carboxylic acid and an alcohol in order to produce that ester. And then B was a cyclic one. The only error that I saw mostly was that most people, a few people didn't have the right number of carbons on there. And this is not evident from this, but there should be 1, 2, 3, should be 6 carbons on there. 1, yeah, 6 carbons on there, starting at underneath the carbonyl group. Write and name the structures of the 2 different monomers that can be used to form, it's basically PEG or polyethylene oxide. So you've done this one several times now, so you should know it. It's polyethylene glycol. You've got the alcohol groups on the end, and the other one is that cyclic structure, which is ethylene oxide. Again, some people draw some quite funky structures in there. It's fairly straightforward. I'm not trying to catch you out with anything there. Draw the repeat unit structure of the polymer produced by ring opening polymerization. So it's pretty straightforward. You can have the true ring opening structure where you open everything up and just do the continual units, or you can break it down into 2 separate units there. What would the average molecular weight of polyethylene terephthalate, PET, if it were carried out to 90% conversion, place a box around the final answer? And it's pretty important that you do place a box around the final answer. And even when it comes to exams, I'll try and remind you that sometimes people write so much, and it's unbelievable. Like, some people write so much equations, they write all the equations in, they give me a full comprehensive overview of what degree of polymerization is, what the molecular weight is, what the NN. I don't need all that. If I'm asking for a specific answer, just give me the specific answer. I don't need your whole interpretation of what's going on, and that will take time in the exam. In fact, actually last semester, we correlated some of the time that people were taking to finish the exams with the amount of stuff that they were writing that was never going to gain them any marks. So I'm pretty keen on just getting the answer that I need, and that's it. I don't think you don't need to do anything. If I say, for example, I know I'm veering off a little bit from here, but if I say, for example, give me 2 disadvantages, if you give me 6, then I'm only going to give you 2 marks, assuming 2 of those are right. But what I will do, if the other 4 are wrong, then I'll start to take marks off for it. So I've asked for 2, give me 2, don't give me 6. So keep these answers as concise as possible. So 90% conversion, pretty straightforward, 1/1 minus P, 1/1, 0.9 times 10. And then we do the molecular weight of the monomer, which is 192 grams per mole. Multiply those 2 together, get 1,920 grams per mole. So there is a little bit of discrepancy there. So some of the I think the most errors that are made are calculating the molecular weight of the polymer in the first instance. Make sure that you calculate the molecular weight of the polymer and not the structure of the monomer with the OH or N groups on those things, because those don't count within the structure. 99% conversion. So again, straightforward, 1/1 minus 0.99 equals 100. 100 times 192 is 19,200 grams per mole. What is the DP of polydioxone of average molecular weight? 125,000 grams per mole. Place a box around the final answer. So there's your answer there, 1225. And what is the percent conversion of the polymer described in question 10A? Place a box around the final answer. So it's 1 minus 1/1225, and that equals 99.92%. So it's just a rearrangement of that original degree of polymerization equation. So here, these, I think most people actually got these correct. I'm not going to go through all these. I'll say the one that the one that most people slipped up on, if you did slip up, was C, and that's because they wrote CCC, GGGG, CCCC, DDDD, when D was not even in the original name. So it's fairly straightforward. I wasn't asking for endless rows of these things. Just as short as you can make them is ideal. Okay, so that's gone through all the notes for those. Again, I will be around over my office hours today. So if you do want to come and see me about your grades or anything, then let me know. So now we can go on to finishing this last one. So we've actually only got like a few slides here, I believe, which is good, but some of these slides are more about you thinking about the answers. So we're talking about glass transition temperature, and we're talking about characteristics of the polymer which change that TG. Now, there is a relationship between the TG and the TM. Both are affected by polymer structure, and factors that increase the TG also result in an increase in the TM. Now, polymers with low TGs have low TMs, and polymers with high TGs have high TMs. There is an exception, and PDMS is one of the exceptions there, and that is an exception due to the flexibility of the bond itself. Now, for symmetrical polymers, the TG over TM is equal to a half, so there's a larger difference between the TG and the TM. For unsymmetrical polymers, the TG over TM is around about 3/4, and there's a smaller difference between the TG and the TM, and they're just general, right? They're just general terms. So the TM mostly depends on molecular symmetry, and the TG mostly depends on the structural rigidity and secondary intermolecular forces. So if you have disubstituted molecular symmetry, you see an increase in the molecular symmetry, which causes a decrease in the TM and a decrease in the TG. And there's two examples. There's the polyvinyl chloride and the vinylidene chloride, but you've seen those ones earlier on. Now, I'm keen to get some practice in with some of these, so I believe that the more of these you see, the more you'll be able to interpret what the TG is. The questions that we ask, and you'll see this in your homework assignments, which I'll give out on Wednesday, is more comparison, right? So I don't need to know explicit numbers. I just need you to tell me whether something is higher than lower than a standard or a comparison molecule in there. So this is how they're presented, and this is how they will be presented on the exams and the homework. So why are the TGs of the two polymers below different? Assume similar molecular weight and processing conditions. So this first one is called PHB, and the second one is called PHV. So can anyone explain why PHV has a lower TG than PHB? And all it is spot the difference. What is the difference? Let's start there.
One has a longer pendant group, a bulkier pendant group.
Yes, good, good. So what does that do? What does that do to the chain? Does it increase the flexibility or does it decrease?
Decreases TG. Right?
Yes, that's right. That's correct. So because it has that long flexible branch and it's only extended by another methyl group, and we see a decrease in the TG there. So the second one, which would you expect to exhibit a higher TG and why? Again, similar molecular weight and processing conditions for both. So we're not thinking about critical molecular weight or anything. So which one would be higher?
The left one.
Why?
Because the extra benzene groups are less flexible than the carbons on the right.
Correct. Yeah, so the left-hand one actually is called PEEK. It's a common 3D printer material. It actually has a TG of 143 degrees C. And where the other one on the right-hand side is polyethylene terephthalate, PET. and that has a TG of 61 degrees C. And as rightly pointed out, you can see that in the peak, there is a lot more rigid benzene groups in there, which are directly in the backbone. So that will cause an increase in the TG. Good. So the main thing is spot the difference. What's the difference between the two things? And that is nearly where you can draw your answer. So third one, which would you expect to exhibit higher TG and why? Note similar molecular weight and processing conditions. So the one on the left-hand side is nylon 12. And the one on the right-hand side is polycaprolactone, PCL.
The one on the right would have the higher TG because it's less flexible. The one on the left has a really long carbon chain. And also the functional groups that like the carboxyl or the ester and the amide, the ester is more uniformly spaced.
So I should mention this. When it comes to the exams, that was a particularly constructive comment that you made. It's not the right answer, but you would still get a partial credit for the comment. So that makes sense. Now, the difference is with this, and the overriding factor with this is that the one on the left-hand side in the nylon 12 can undertake intermolecular hydrogen bonding, which makes it stronger or makes it have a higher TG than the PCL that can't undergo that. But you are right. The chain lengths are pretty big, and that increases and contributes to the flexibility. So this is a slight different one, but in this case, a hydrogen bonding overrides that. But it's good. It's a good explanation. That's what we need. So we need to know that you're thinking about it. It's good. So then the next one is polymethyl methacrylate. Polymethyl acrylate, PMA. And the one on the right-hand side is polyacrylic acid, PAA. Which one has the higher TG? So let's start. What is the difference between those?
We have the methyl group on the PMA.
Yeah. So actually, we have the methyl group on the bottom, which essentially is replacing the hydrogen on the OH there. And then you also have a methyl group added to the top carbon there. Sorry, was you going to say something?
Oh no, I was just agreeing. Like I didn't know.
Oh, you're agreeing with it. Thanks. I appreciate that.
On the, yeah.
So okay, so there's a difference. Now, what can happen with PAA that can't happen with PMA? Based on exactly, good. So the PAA can undergo strong hydrogen bonding, and in fact, actually, it's a less bulky pendant group. So that means that the TG of the PAA is greater than the TG of PMA. We can keep going all day with these ones, but I think this is the best way to learn it. And I think the more you see, the more you'll get an idea, because there's only a limited number of polymers we can keep showing. So rank in order of TG, 1 the highest and 3 the lowest, and why. So I'm going to give you a little bit of time to think about that. So these ones do come up as well, where you have to put a rank in. on there. So who wants to throw a guess out? Which one will have the highest TG? Yes, the middle one. Why is it the middle one? Has the most rigid backbone. Good. So that is peak again, which we've already seen. And the TG of that is 143 degrees C. So the answer to that is it has rigid groups in the backbone. Now, which is the intermediate TG out of those three? Is it PET, which is the one on the left-hand side, or is it PDS, which is on the far right? PET. Good. Why is it PET?
Because it's more rigid than PDS.
Yeah. So it's still got those benzenes in the backbone there, and it still undergo the dipole-dipole intermolecular forces. So that will have medium rigidity, so because of those cyclic groups. So that the PET, the one on the left-hand side, has a TG of 61 degrees C. And then the one on the far right has the lowest, PDS has the lowest TG at minus 10 degrees C, just because it has that highly flexible backbone in there. So then let's move to the one below. Which is the strongest secondary force for all the polymers above. So it's dipole-dipole for all of them. I've answered that for you. I've just answered that anyway. But what about A, B, and C? Can we say which one is the highest TG, which one is the intermediate TG, and which one's the lowest TG for those? Take a couple of minutes to think about it, and then we'll. Okay, so can anyone offer an answer for that? Which one's the highest TG?
C,
Yes, good. Why?
because it can do hydrogen bonding and it has a shorter alkyl chain than B, so it'll be less flexible.
Exactly. Combination of two things there. Great. So good. Which one's the intermediate? B. So B still undergoes hydrogen bonding, but you've got a bit more of a flexible backbone in there compared to C. And then A is the lowest, and it's the lowest because it still has a relatively long CH2 segment in there, and it can only undergo dipole-dipole intermolecular bonding, so it's fairly flexible. Good. So which would be predicted to exhibit a higher TG and why? So there's two molecules in there. Which one has got the highest TG and why? Any answers?
B, because of the rigid rings in the backbone.
Yeah, and it's a bit confusing, that one. I think sometimes when you have the CH2s with the small 8s or what number next to it, some people don't recognize that, but you are correct. Because B has those rigid groups in the backbone and they're relatively frequently spaced throughout that will exhibit a higher TG than A. A does have dipole-dipole, so I'm just telling you what the strongest intermolecular forces for A is. It's dipole-dipole. But they do have those long flexible chains in there. So you'll see a few more. So this is just a list of the different TGs for polymers in here. So you'll see a lot more of those examples in the homework and maybe a few on the in-class, which we'll do maybe later on this week. But the more practice you can get, the better on those things. So we're going to give you as much as possible. But it seems to be coming along. So you don't know it, and it may not be obvious, but now you're having an understanding of how the different structural makeup of polymers is affecting their physical properties. In the next segments, I think 6, 7, and 8, we actually go through more mechanical properties, which are important for the biomedical usage. But you're trying to build up kind of a broad context to how these polymers are structured in order to undergo specific biological applications. So we're getting there. Good. I'm glad we got those ones. So that's it for today. We'll post lecture. So we're now moving on to module 6, and then we will do the in-class maybe on Friday. But again, you're working groups and you have your books there. I don't think it's too long. Good. Is there any questions?
Yeah, I had a question about classifying which, or could you go up to the classifying which one is with the TGs? Yes, the strongest. One more slide down. Yeah, so I'm just fundamentally struggling with A, B, and C, the one below, how we see which one, or how C is the greatest TG, right?
So if you, it'd be easy to show you because I don't have my pencil, but see where it says on C, where you have those CH2 chain right in the middle, and it's got a little 5 next to it.
Yes.
So that'll mean that there's 5 carbons in that chain. Now, compared to B,
Yes.
if you look in the same position, that's got 11 in there. Now, we know that having those carbons in the chain is going to increase the flexibility. So we know that the increased flexibility is going to decrease the TG, therefore C has a higher TG. But they both demonstrate hydrogen bonding, it's just that the spacing is different between them. And then A is a kind of a total knockout, wipeout in a way, in that one can only undergo dipole bonding in there.
I guess like because like B, for example, is the TG is lowered and like you're saying the flexibility lowers TG. What's the, I guess, like the fundamental principle behind that? I don't know if I'm missing something, or is that just it?
Well, it depends which level you're looking at it. So it is essentially just that chain in the middle is a lot longer. That increases the flexibility. Therefore, the TG is lower than C.
So it's able to like, I guess like the way I'm looking at it is like the bigger the molecule, the harder it would for it to change into a rubbery state. Like, I don't know if that makes sense.
Yeah, I mean, so what we're trying to do, and when we're changing it into the rubber state, we're trying to break it down, right? We're trying to start to get rid of some of those secondary intermolecular forces.
Mhm.
Now, if you look at B, we know that B and C both undergo hydrogen bonding, but B, the spacing of those hydrogen bonds is a lot bigger, right? So it's easier for us to move from a glassy to a rubbery state with that. Compared to C, where they're actually a lot less broadly spaced.
Mm-hmm. Okay. And then
You
yeah,
sound unsure.
yeah. I mean, it's fine. I think I'm just trying to. So like, I don't know. I can't.
Yeah, I don't know which level. I don't know how. I mean, you can't look into it. I mean, you can look into it as much as you want, but that is the general gist of it. With those two, is if you see those longer chains in there, you're going to increase the flexibility. Increase the flexibility is we're going to reduce the TG.
Okay.
Okay.
Yeah, I'll sit with that concept. And
I would just keep looking. I would keep looking at it and then going through and then going back to the notes that we made before. I honestly do think the best way to do this is just to keep doing them and doing them, rather than kind of learning the exact principles, because you'll spot then. I treat it like spot the difference, honestly. I look at one molecule, then I look at the other, and I go, what's changed?
Right.
Is hydrogen bonding in there? Yes, hydrogen bonding in there. Well, I know that's going to be a high TG straight away. What's the flexibility of the backbone look like? And in this case, the B is extended by lots of different carbons compared, well, 6 extra carbons compared to the C. Therefore, I know that that's going to result in an increased flexibility and a lower TG. So C must be higher in this case. It's almost just like a detective, just trying to work out what the difference is between these things. And there'll be some that are a little bit more difficult, like a PET, the one above, being the intermediate, is a little bit more difficult because, yeah, it still has a fairly flexible backbone, but actually just because it's got that phenyl group in, phenyl benzene group in there, that's going to contribute to the rigidity quite a lot. So that's why it always kind of ends up intermediate. There's only dipole, but if you look at the rest of those structures there, they're all dipole, right? So if one was hydrogen bonding, I would look at that straight away, right? And I go, oh, it's hydrogen bonding.
And that would have the highest.
You'd presume so, yeah. I mean, it depends. I mean, if the chain was ridiculously long, some of the things, it's all about the justification that you give, right? And that's the important thing. So you do get partial credit, even if the justification might not, be for the correct answer.
Okay. All right.
But it's got to be realistic justification, right? You can't just add.
Okay. Thank you.
Yeah, no problem. Anything else? Are we done? Okay, good. Well, stay safe and we'll catch you on Wednesday.